In today's session, we'll be developing the power and torque equation of a synchronous generator. Power and torque equations. The power and torque equations of a synchronous generator are very important to understand the behavior of a synchronous machine. And since we know that synchronous generators are used in power plants, the power equation is very necessary. Uh, so this is the power flow diagram of a synchronous generator. The power flow diagram of a synchronous motor will be in the reverse order. So here we can see that P in is the input power, that will be the mechanical power in this case, that will be applied to the shaft of the motor given by torque applied into the speed of rotation. So there will be some stray losses, there will be friction and windage losses. Now these losses will be at the start of this machine, since the friction will be the first type of loss encountered in uh, while making the shaft of the rotor rotate by the mechanical energy of the water or steam. Once we move from friction losses, we have the core losses, and then we have the armature copper losses. There will be voltage will be induced in the armature of the windings. So the copper losses taking place in the armature winding uh, will be I square R losses, and the output power will therefore be given by root 3 VTIL cos theta, where VT and IL are the line voltage and line currents of the at the terminals and from the terminals of the armature circuit. So we have already studied these different types of losses. We know what's core loss, that comes of eddy current losses and hysteresis losses. We know the copper loss because of the resistance of the windings given by I square R losses. P converted is actually the power that's available at the terminals of the uh, at the start of the armature winding. Now, since this is the actual power that is transmitted to the armature windings, but there are certain losses taking place in the armature windings itself. They are the copper losses. So minus them, we have the output power. So we can write various equations of this as P induced is torque, that's the applied torque, into omega m. P converted here, since as I said to you, it's the actual power getting induced into the armature circuitry. So if EA is the induced voltage in the armature and IA is the current flowing through the armature, we can say 3 EAIA cos del cos of gamma will be the converted power, where EA is the induced voltage in the armature. It is not the terminal voltage of the armature. It is the voltage that's induced in the armature. It is the IA is the armature current. And if these are phase quantities, we can say it is 3 times. If we are representing in terms of line quantities, this will become root 3 times. And delta is the angle between EA and gamma is the angle between EA and IA. And output power is 3 VPH IPH cos theta, or we can in terms of phase quantities, or we can write it as root 3 VTIL cos theta in terms of line voltage and line currents. Similarly, the reactive power. This is the real power that is generated from the synchronous generator. The reactive power that will be generated can be given similarly as 3 VPH IPH sine theta or root 3 Vt IL sine theta. So this is the reactive power component. So here P induced, Pn represents the input power given by the mechanical rotation of the device and the torque applied by the uh, mechanical source of energy. P converted is the power input to the armature windings. P out is the output power from the armature winding. So the difference between P converter and P output is actually the armature copper losses, I square R losses taking place in the armature windings. So we can similarly derive the reactive power equations as well. Now we'll assume that RA is much smaller than the uh, synchronous reactance of this machine. We are saying that the armature resistance is less than the synchronous reactance in case of a synchronous generator. This will actually help us derive an output power equation that will be very useful. Uh, that's actually very useful for stability studies and other equations of a synchronous machine. So we are assuming that the armature resistance, this is actually factually true, that armature resistance of a machine will be much less than the synchronous reactance of the synchronous generator. Now, at this condition, what will be the phasor diagram? This is the terminal voltage Vt. This is the armature current or a lagging load. If there were an RA component, IaRa would have been in this direction, and IaXa, J times IaXs would have been in this direction. Since there is no uh, component, that is IaRa is ignored in this case, we are ignoring IaRa, this J times IaXs will simply shift here. So this will be J times IaXs. Then in that case, the resolution of these vectors will give us the induced voltage EA in the armature. Let me write this as Vp, the phase voltage. So we have we have actually already seen that the angle between IA and Vp is nothing but theta. The angle between IA and EA, we have said this is gamma. Let the angle between EA and Vp be delta. In that case, if we draw a perpendicular line here, this portion is what we are interested in. So this angle will also be theta. So accordingly, we can say this vector, the vector here, will be IaXs times cos theta. Or in other words, we can also solve it in terms of EA as EA sine delta. So this vector can be either be resolved as IaXs cos theta or as EA sine delta. In that case, we can say that IaXs cos theta is equal to EA sine delta, or which implies Ia cos theta is EA sine delta divided by xs. We have already said that the equation is 3 VPH IPH cos theta. So real power is 3 VPH IPH is actually the armature current. 3 VPIA cos theta is the power. So if we have we can substitute for IA cos theta. So we will get 3 VP EA sine delta divided by XS. So this equation where we are having P is equal to 3 VP EA sine delta divided by XS, or it can also be found in terms of the line voltage root 3. So we have here this equation states us that for maximum power, sine delta will be equal to 1. At that time, our maximum power will be 3 Vp Ea divided by Xs, where delta will be 90 degrees, such that sine delta is 1. This is actually known as the stability. This is known as the static stability limit of the generator. What this means, here delta is the angle between the generated voltage and the terminal voltage. Now in case there is no resistance, that means there is no armature, there is no copper losses, armature copper losses. This also means that P converted at this time will be equal to P out. So that P converted equal to P out is actually given by this equation at that time. 3 Vp Ea sine delta divided by xs. Now for sine delta equal to 1, that is the maximum we can have, the maximum power point we can obtain from the synchronous generator is at delta equal to 90 degrees. Beyond this, if we increase delta beyond this, the synchronous generator becomes unstable and uh, it goes out of synchronization. So the maximum power obtainable from the synchronous generator is 3 VPEA divided by XS. So it depends upon the synchronous reactance of the synchronous machine. Now here it needs to be said that in practical circuits, delta never exceeds 15 to 20 degrees. The limit that this angle has is 15 to 20 degrees, and this delta is actually known as the torque angle, the angle between the applied induced voltage and the terminal voltage. That's known as the torque angle here. A full load torque angle of 15 to 20 degrees are actually more commonly seen in real machines. We have actually, so this is the power equation that we mostly use in case of synchronous machines. 3 VPH IPH cos theta. We need to find out the real power or the reactive power. We can also assume that the armature resistance, we can neglect the armature resistance. At that time, we can simply say that P will be given by 3 VP ES sine delta divided by XS. So it depends upon mainly the synchronous reactance of the machine. So as I had already stated to you that synchronous reactance will play an important part in determining the stability of the machines. Now we also know that from previously we have already studied that K is nothing but the cross product of the torque induced is nothing but the cross product of PR and BS. Now in this case, BR will be BR is the BR is the magnetic field produced by the rotor, and it will be in line with EA, while as B net will be the net magnetic field that will cause uh, that will cause that after subtracting the armature reaction effect, we'll get the net magnetic field. Along the net magnetic field, we will be having the V phase component. So if we say that this is BR, this is BS, this is the net magnetic field produced by the interaction of the rotor magnetic field and the stator magnetic field here. BR along the direction of BR is also EA, whereas along the direction of B net is the phase voltage, the resultant voltage B phase, whereas along the direction of BS will be the stat uh, stator magnetic field induced voltage E stat. The resolution of those two vectors is B phase. So torque induced will be equal to BR cross B net. We can see from this diagram that since we have already said that the angle between EA and V phase is delta, that's the torque angle. So the angle between BR and B net is also delta. So in other words, we can put this as BR B net sine delta. So delta is the angle between the rotor and the net magnetic field. Also, as already stated, as it is known as the torque angle of the synchronous machine. Alternatively, we also know that P converted is equal to torque applied into the measured speed, uh, torque induced. P in is torque applied into omega m. P converted is torque induced into omega m. Since we already have said that P converted is 3 Vp Ea sine delta by xs, that means this is equal to torque induced into omega m. That gives us torque induced will be equal to 3 Vp Ea sine delta divided by xs into omega m. So this is the equation of torque induced. We can use this equation. This is the equation used for power. So just having a recap, this is the power flow diagram of the synchronous machines, where we have the stray losses, friction loss of the synchronous generator rather, and then the armature copper losses. The reverse flow diagram will be true for a synchronous motor, where the input power will be root 3 VTIL cos theta and output power will be torque applied into omega m. So P converter, as I said to you, it is the actual power that's applied to the input of the armature winding. It is not the power available at the output of the armature windings, at the terminals of the armature windings. So at the input we have the voltage EA. So accordingly we can derive the real power as 3 IA cos gamma, where gamma is the angle between EA and IA. The output power will be simply given by root 3 VTIL cos theta. Now we have assumed that for a very low armature resistance, much less than the synchronous reactance of the machine, we can see that using this using this Phasor diagram, we have derived that Ia xs cos theta is equal to Ea sine delta. Substituting this Ia cos theta in the actual equation, we get the equation 3 Vp Ea sine delta divided by xs. So this actually is the power equation relating the two voltage, that's the input, that's the induced voltage in the armature, and the output voltage available at the armature terminals. And delta is the angle relating the uh, armature voltage and the phase volt, the induced voltage and the terminal voltage of the armature. For delta equal to 90 degrees, sine delta will be 1, so we'll get a P max that will be given by 3 Vp ES Now, as I said to you, this is known as the static stability limit. For delta greater than 90 degrees, the synchronous machine will fall out of synchronization. That means it becomes unstable. But typically, for practical machines, we do not have a we have a typical value between 15 to 20 degrees up to 30 degrees. Uh, Also deriving for the torque equation, we know that P converter is equal to torque induced into omega m. So substituting for P converted, that's 3 VPAIA by XS sine delta is equal to torque induced. We get this equation for torque induced. So this is the power and torque equations of a synchronous generator. Same equations hold true for synchronous motors, obviously. We can also find out the torque max from here by substituting sine delta equal to 1. So in the next session, we'll be studying the characteristics of synchronous machine and accordingly deriving the parameters of a synchronous machine.